Okay, in this lesson, we're going to be talking about Extrema, which is your maxes and mins. This is a rather long lesson, so I'm going to make sure that I try and break it down into two parts, at least maybe three. So the first important theorem that we're going to look at is called the mean value theorem. It says that f of x has to be continuous on the closed interval and differentiable on the open interval. There exists some point where the derivative is equal to f of b minus f of a over b minus a. Now remember, we said that this was the slope of the secant line. Okay. So this graph is just a visual. So your secant line is drawn between 2 points. So if your function is continuous and differentiable, there's some point in between that the slope of the tangent line, the derivative, is equal to the slope of the secant line. Okay, so our first example, it says given the function f of x is equal to x cubed plus 2x squared minus x on the interval -1 to 2, find a value of c that satisfies the mean value theorem for derivatives. Okay, so we know that this is continuous, it's a polynomial function, and it's differentiable because you can take a derivative of it. So we're going to take the derivative. So our derivative is 3x squared plus 4x minus 1. Now, we also have to plug in and find our f of a and f of b. So f of -1 and f of 2. I want to plug into that function right there. So -1 cubed is -1 plus 2x squared minus x. Okay, and you're plugging in a -1. Minus x. So for the second time, I'm using my calculator. So I got 2 and I got 14. So when we go to do this, we're going to do 3c squared plus 4c minus 1 is equal to 14 minus 2 is 12 divided by 2 minus a -1. 12 over 3, which is equal to 4. Okay, now we're going to move this over to the other side, so we get 3c squared plus 4c minus 5 is equal to 0. Let's see, does this factor? Factors of 5, I don't think it factors. So what we're going to have to do is use a quadratic formula. So -4 plus or minus the square root of 16 minus 4 a c all over 2 a. Okay, so you can do 16 minus 4 times 3 times -5. Okay, 76. So our answer comes out to be -4 plus or minus square root of 76 over 6. Now, that's your value of c. And we need to make sure that this lies in the interval. So -4 plus square root of 76 over 6 is 0.786. That works. -4 minus square root of 76 divided by 6 is a -2.11. So that one's out of the interval. So your only answer is going to be -4 plus square root of 76 over 6. Okay, continuing this example. Find a value of c that satisfies the MVT for derivatives, and you're given this function right here. So this is going to be continuous everywhere except for 0, so we're good right there. And it's differentiable because you can take a derivative of it. Okay, so let's take our derivative. So the derivative of x is 1. The derivative of this is going to be -27 over x squared. Now you're going to want to get a common denominator here. I just did around the world. Okay, so we're going to plug in f of 3 and f of 9. If I plug in a 3, 3 plus 27 divided by 3 is 9, so it should come out to be 12. Okay, and if I plug in a 9, that should also come out to be 12. Okay, so if I do my f of b minus f of a over b minus a, you get 12 minus 12 over 9 minus 3, which comes out to be 0. Okay, so when we do that, we set c squared minus 27 all over c squared is equal to 0. Now, anytime I set a fraction equal to 0, I'm just looking at the top. I'm just concerned with the top. So I do c squared minus 27 is equal to 0. So c squared is equal to 27, and c is equal to plus or minus the square root of 27. Now, when we do this, we get our final answer. We can't use the negative branch because we're in between 3 and 9. So the only correct answer is going to be square root of 27, which is 5 point something. Okay, so it should work. Okay, on to the next theorem, Rolle's theorem. So Rolle's theorem says that if I have 2 points that have the same y value, there has to exist some point in between where f prime of c is equal to 0, which means we're either have a max or a min. So this is just a good visual to be able to see what Rolle's theorem illustrates. Okay, so your first step whenever you're doing Rolle's theorem is you're going to say f of 0 and f of 4 in this example. Okay, so we're going to plug in our a and our b. So if I plug in a 0, I get 0. If I plug in a 4, I should get 0. So f of a is equal to f of b. Therefore, Rolle's theorem applies. Okay, now we're going to go and we're going to take our derivative of this. So f prime of x is equal to negative 2x plus 4, and it says plug in a c. F prime of c is equal to negative 2c plus 4. And I'm going to set it equal to 0. Okay, so when I solve for c, c comes out to be negative 4 divided by 2, it should be 2. Okay, and 2 is in between 0 and 4, so it works. So that's how you satisfy Rolle's theorem. Now it also says find a value of c that satisfies the mean value theorem for derivatives. So mean value theorem we just said was f prime of c is equal to f of b minus f of a over b minus a. Our derivative is this. Our f of b minus f of a over b minus a is going to be 0 minus 0 over 4 minus 0, which is 0. So our value of c will end up being the same exact thing in this case. Okay, critical points. So we define critical points as where the derivative is equal to 0 or the derivative is undefined. Okay, so let's do a couple examples that deal with critical points. Okay, so we're going to take our derivative. Derivative of this is going to be 30x to the 4th plus 33 times 4 is 132. X cubed minus 90x squared. Okay, now they all have, I guess, a 3 in common. Yeah, they all have a 3 in common and an x squared. So we're going to factor on x squared and a 3. So we get 10 x squared plus 44x minus 30. Those are all divisible by 2. All those are still divisible by 2, so let's make this 6x squared. Let's see, 5x squared plus 22x minus 15. Okay, we should be able to factor that. So, factors of that are going to be 5x, x. Factors of 15, let's see, it's going to be a plus 5 and a minus 3. So we're going to set each one of those equal to 0, so we should get x is equal to 0, x is equal to 3/5, and x is equal to a -5. Those are our critical points. Okay, don't forget about the x squared on the outside. You still have to set that equal to 0. Okay, critical points of this. So what I'm going to look at, if I have a fraction, I'm going to look at the original domain. So this is going to factor to w minus 3. And w plus 2. Okay, w squared plus 1 doesn't factor. Remember that? Okay, so whenever we're doing this, we would have our original domain is negative infinity to positive infinity. X cannot equal to, or w cannot equal to 3 or -2. So those are going to be automatic critical points because they're not going to be defined. So we're going to have a quotient rule right here. R prime of w. So we're going to write the bottom. Derivative the top. Minus, we're going to write the top. And derivative of the bottom is 2w minus 1. All over the bottom squared. Now we already know where it's going to be undefined. We already just dealt with that. It's going to be at 3 or -2. Now what we're concerned with is the top now. So we're going to have to FOIL this out. Okay, so it's going to be 2w cubed minus 2w squared minus 12w. So I'm just distributing. And then get 2w cubed. I'm going to change the sign. -2w cubed. Outer is going to be plus w squared. Okay, I changed the sign. Minus 2w and minus 1. Now we're going to combine all our like terms. The w cubes will cancel. W squareds. Combine those like terms. Minus 14w minus 1. And I really don't think that this will factor, but we can look at our graph just to make sure. So that's our derivative. The only reason we have to simplify this is because we're trying to set it equal to 0. So let's look at the top and see if that crosses anywhere. Yeah, it crosses at somewhere close to 0. I'm using my zeros on my calculator. So I get w is equal to -0.0718. And w is equal to 3. And w is equal to -2, all for your critical points. Now I know that was a little tricky because we had to use our calculator, but you can't be afraid to use your calculator to find your zeros if you don't know how to factors. You should know how to factor this using PSF. Okay, the last little section we're going to talk about in this video is absolute extrema. Okay, absolute max and absolute min. So absolute max and min are the highest and the lowest point on a graph. So in this graph right here, the highest point is going to be here, and your lowest point is going to be over here. Now, we have something called relative maxes and relative mins. Those are going to be the hills and the valleys. So where your derivative is equal to 0. You have a max here, a min here, and this serves as both a relative max and an absolute max because it's the highest point. So your steps are, whenever you find an absolute max or min, is you find your critical points, and you take each one of those and you're going to plug into the original function. The one that has the highest y value is going to be your absolute max. And the one with the lowest y value is going to be your absolute min. So we're going to take our derivative. So we write the bottom, derivative the top. Minus, we're going to write the top, derivative of the bottom, all over the bottom squared. I'm going to find my critical points. So x squared plus 1 minus 2x squared. Now we're not going to get anything from the bottom because it's difference of squares. Sum of squares. Sum of squares does not factor. The top, we will be able to get something. Okay, so we're going to set the top equal to 0. 0 is equal to negative x squared plus 1. Move that over. So x comes out to be plus or minus 1. And both of those points fall into our given interval. So we're going to plug in f of 1, f of negative 1, f of negative 3, and f of 3. So if I plug in a 1, I get 1/2. I plug in negative 1, I should get negative 1/2. Plug in a negative 3, should give you negative 3/10. And I'll plug in a 3, you should get 3/10. Okay, so 1/2 is 5/10. So this is going to be your absolute max. This is going to be your absolute min. That's how we do absolute max and min problems. Remember, if it says value, you're looking at a y value. Okay, same process on this one. We're going to take our derivative and find our critical points. So we get 2x minus 2, set it equal to 0. You get x is equal to 1. And we're going to plug in our critical points and our endpoints into the original function. Plugging in a 1. 1 minus 2 is a negative 1, plus 5 is 4. Negative 2 squared is 4. 8 should be 13. 25 minus 10 is 15. 15 plus 5 is 20. Let me just double check that and make sure. It's been a while since I've had to do mental math. 1, 2, and 5. Okay, so this is your absolute min, and this is your absolute max. Okay, now the last thing we're going to look at is a little graph. So we're going to label on our graph where we have absolute maxes and absolute mins and your local extrema. So this is going to be your absolute max because it's your highest point. This is going to be your absolute min because it's your lowest point. Now, we will have a local max over here. We'll have a local min here, or relative min. You know, it uses both those names. And this is also going to be a local min. Okay? So that's how we correctly label absolute maxes and absolute mins, local maxes and local mins. In the next section, we're going to look at how to interpret the first derivative, second derivative, and intervals of increasing, decreasing maxes and mins, and concavity and inflection points. So hopefully this helped you out a little bit, and hopefully you have a good night. Thanks.